It is the evening of March 8, 2014. A scheduled overnight commercial passenger flight departs Kuala Lumpur, bound for Beijing. The aircraft operating the route is a Boeing 777-200ER, climbing through clear skies with no significant weather systems. On board are 227 passengers and 12 crew members. At 39 minutes past midnight, Malaysian Air Traffic Control loses contact with the aircraft. To the controllers on the ground, the plane has vanished. Yet the aircraft continued to fly for nearly 7 more hours over the open ocean. Investigating this flight requires treating it as a strict mathematical problem. With no physical wreckage found for years, we have to rely entirely on surviving metadata to trace its final path. Aviation tracking relies on 2 distinct layers. Primary radar bounces radio waves off physical objects, while secondary tracking relies on the aircraft actively broadcasting its own data. Commercial jets use a system called ACARS, the Aircraft Communications, Addressing, and Reporting System. This operates over satellite or radio links to send automated status updates about the plane's engines and fuel levels to the airline. Simultaneously, a Mode S transponder actively broadcasts the aircraft's identity, altitude, and speed to civilian ground stations. Standard civilian air traffic control screens are designed around these active pings. They need the aircraft to participate in its own tracking. If the transponder and ACAR systems fail or are manually deactivated, the aircraft stops transmitting. To a civilian radar operator, it effectively ceases to exist. Determining exactly when and how these specific communication networks went dark gives us our only objective timeline of the events unfolding in the cockpit. The flight takes off from Kuala Lumpur at exactly 0042 Malaysian time. Operations proceed normally. At 0106, the ACAR system transmits a routine automated packet detailing the total fuel remaining, 43,800 kilograms. 13 minutes later, at 0119, the cockpit makes its final voice contact with ground controllers as the plane approaches navigational waypoint Igari. At 0121, the Mode S transponder abruptly stops transmitting. This shutdown happens precisely at the boundary separating Malaysian airspace from Vietnamese airspace. Going dark at the exact moment of an airspace handover creates a massive window of confusion. Controllers in both countries assume the other has tracking responsibility, which severely delays any emergency response. Civilian screens aren't the only tracking method. Malaysian military primary radar, which tracks raw radio wave reflections rather than active transponder pings, continues to see a physical object in the sky. This map traces the military data, showing that after passing waypoint Igari, the aircraft executes a sharp left turn, diverting southwest. During this maneuver, radar records severe altitude fluctuations, with the aircraft climbing to 35,700 feet before dropping back down toward 31,000 feet. The physical flight path then cuts directly back across the Malay Peninsula, navigating along established air routes. The last known primary radar contact occurs at 0222, when the aircraft flies out of range over the Andaman Sea. This series of calculated maneuvers across multiple waypoints eliminates the possibility that the aircraft suffered a sudden mid-air disintegration. It was still flying and navigating. This brings us to the Aircraft Satellite Data Unit, or SDU. This is the terminal that allows the plane to route messages over commercial satellite networks. Data logs show that between 0107 and 0203, electrical power was cut to the SDU, but at 0225, power is restored. As the SDU boots back up, it automatically transmits a logon request to the Inmarsat satellite network to re-establish a connection. This reboot occurs exactly 3 minutes after the aircraft leaves the physical range of Malaysian military radar. An in-flight SDU power cycle is highly abnormal. It requires either a localized electrical failure that affects only this specific unit, or a deliberate manual reset of the breakers in the equipment bay. Once reconnected, the Inmarsat network follows its standard protocol. If the ground station hears nothing from the aircraft for an hour, it sends an automated status request, a ping, to ensure the terminal is still active. This animated diagram illustrates a signal ping traveling from a ground station up to a satellite, down to the aircraft and back. Investigators measured the burst time offset the exact microsecond difference between when the ping is sent and when the response is received. By calculating the speed of light against that transit time, investigators determine the precise physical distance between the satellite in orbit and the aircraft. You cannot pinpoint an exact coordinate with this distance, but you can draw a circular arc on the Earth's surface, indicating all possible locations where the aircraft could be. To narrow down where on that arc the plane was, investigators used burst frequency offset, which measures the Doppler shift in the radio signal. This waveform animation demonstrates how the radio wave compresses as the aircraft moves towards the satellite and expands as it moves away, revealing its relative speed and heading. The recorded frequency adjustments prove the aircraft did not fly north towards Asia. It turned south, maintaining a steady track into the remote Indian Ocean. The hourly handshakes continue until 0819, when the aircraft sends one final unprompted logon request. Based on the fuel logs, 0819 aligns precisely with fuel exhaustion. When the engines flame out, the plane's ram air turbine deploys into the airstream to provide emergency power, rebooting the SDU one last time before the flight ends. With the telemetry data mapped, investigators apply it to the two most prominent theories: an unresponsive crew due to hypoxia, or deliberate human intervention. The Australian Transport Safety Bureau primarily evaluated the hypoxia theory, where a sudden depressurization event incapacitated everyone on board. A crew rendered unconscious explains why the aircraft flew a steady, automated course along the southern arc for 5 hours without any deviation or communication. However, a depressurization event does not easily account for the transponder and the SDU failing at different times, while the flight systems remained completely functional. This timeline charts the deliberate intervention theory, stacking the exact minute the transponder shut off, the crossing of the airspace boundary, and the SDU power cycle. A pilot intentionally padding communications explains why the transponder went dark at the exact moment of the airspace handover, and it accounts for the localized manual reset required to reboot the SDU. The metadata heavily implies a systemic, intentional severing of the aircraft's tracking equipment, but data alone cannot mathematically prove intent, leaving the root cause unconfirmed. Verifying exactly what happened in that cockpit requires the flight recorders, but the search ran into severe physical constraints. Finding the black boxes relies on underwater locator beacons attached to the recorders. In 2014, these legacy beacons had a maximum acoustic range of 3,000 meters and a strict battery life of just 30 to 40 days. Against the immense depth and vastness of the southern Indian Ocean, those 30 days expired long before search vessels could thoroughly map the correct zone. The inability to locate the wreckage forced the global aviation industry to confront the fragility of its tracking infrastructure. Regulators enacted sweeping mandates. Underwater beacons must now operate for 90 days. New aircraft designs must incorporate ejectable flight recorders, and planes flying over open oceans must report their precise position every 15 minutes. The forensic void left by MH370 initiated a permanent architectural shift. It ensured that a modern commercial airliner can never again slip completely off the telemetry grid.